Hello everyone, this is Amal Naruto. Welcome to my channel. So today I'll be explaining the topic which is nothing but the most important one in the linear regression, that is multicollinearity. So this is the most important topic. So now I'm gonna explain this topic here. So first of all, what is meant by multicollinearity? So for that I'll draw some kind of a graph here. I'll plot something. Okay. So this is my okay, first of all, let me draw my data set here. Okay, first let's imagine this is our data set. Okay, so this is our data set, and this is my y variable, that is dependent variable y. Okay, so these are all my independent variables. For example, I have x1 and I have x2, I have x3, I have x4. Okay, let's imagine this. Okay, so x1, x2, x3, x4, these are all the uh, independent variables here. And this particular y is nothing but the dependent variable, which can also be called as a response variable. Okay, so if I want to plot my independent variables, let's say I want to plot this x1 and x2 on this plot here. So I'll say I'll take this x1 on my x-axis and I'll take x2 on my y-axis. So if I want to plot something here, so the if the correlation between these two variables, let's say if that correlation forms a straight line here, okay, so see we can observe some kind of a shape here, which is nothing but a uh, straight kind of a shape. Okay, so this is not a perfect straight line, but there is some kind of a positive trend overall. If you just observe here, the the graph is actually showing the positive trend here. That is this kind of it is in this kind of a shape here. That is right. So when you observe these kind of a positive correlation between any independent variables, that is x1 and x2, you can surely say that these two variables are highly correlated with each other. So usually we will find out whether our independent variable is having high correlation with our dependent variable or not. We try to, I mean, we are interested in testing with that. For example, if I have any correlation with x1 and y and x2 and y and x3 and y and so on, okay, and x4 and y, so we will be interesting in finding out all these things. Why? Because if we find out that x1 is actually having high correlation and in the second place x3 is having high correlation, then what we can do is we will just pick only those variables, that is only x1 and x2 here in our model building process, because considering the remaining variables, that is x2 low which is having some low correlation and x4 is having very low correlation, considering these x2 and x4 in our machine learning model is absolute meaningless. Why? Because these are actually failed to explain the variables, that is our dependent variable. So what we can do is we only consider this x1 variable and x3 variable in our machine learning model building process. Okay, so this is the scenario in general. But here, when I try to plot the x1 and x2, I'm observing some positive trend, that is nothing but a positive correlation. It's having some positive correlation here. So what is it actually indicating? It's saying that x1 and x2 are related with each other, right? So if this is the case, then our model will definitely can produce some kind of a noise here, right? For example, there is some kind of a noise. For example, if I try to plot the x-axis and the y-axis, and this is my x, okay. These are all my independent variables, that is x1, x2, x3, and so on. And if I try to plot, okay, for example, let's say this is x1, this is x2, and this is x3. Let's imagine this is x4 here, okay. If this is the case, and if I try to plot, this is the y here, and if I try to plot, there won't be any kind of much straight line. There would be some kind of a difference. I mean, see, I'll try to see, this would be the plot here. What do you mean by this? Actually, in the linear regression, the desired shape of a line, I mean, the desired shape of a model would be the simple straight line, right? So this would be the desired line here. But this is not the case. Why? Because if I try to draw some kind of a straight line here, all my points are actually not falling on that particular line. They are somehow falling just beside that particular line. That means there is some kind of a spread in all over, I mean, in the data points all over. So what is mean by that particular spread here? That spread is nothing but some kind of a noise. We can call it as some kind of noise. So that noise is nothing but the unexplained variance. So that noise is nothing but unexplained variance. So what is meant by that unexplained variance? We can't control this unexplained variance. Okay, our model can't explain this particular variance, that is unexplained variance. Okay, so how does it actually happening here? This is actually happening due to the fact that x1 and x2 are actually correlated, highly correlated with each other. Okay, so if we try to remove this x1 and x2 from our data set, then this would not be the case. Probably, maybe this would be the case here. For example, maybe this would be the scenario. So if we try to draw a straight line here, so all the points will come just somehow closer towards the line here. I mean, there would not be any kind of much spread when you compare this particular spread with the previous spread here. Here it is having high spread. Okay, but when you try to plot again after removing x1 and x2, then you will find somehow some less spread, okay, than the previous one. So how is it actually happening? This is actually happening due to the reason that x1 and x2 are correlated with each other. This is nothing but the multicollinearity. So this is the concept of multicollinearity. If you want me to show something, okay, I'll show you this particular plot here. So earlier we have plot something like mpg, okay, mpg, and this is the y prediction. Okay, so this is the y test of mpg, and this is the y prediction. So this is the predicted one, and this is the actual one. So on the x-axis we are having some kind of actual one, and on the y-axis we are taking the predicted one. Our model has predicted. So if I try to plot the plot, if I try to plot, see what is happening here. Here, if I try to draw a straight line here, then see, all the points are actually, if I mean, the ideal case would be the all the points should actually fall on this particular line itself. They should be exactly on this particular line. But is it the case here? No. Why? Because there is having some kind of spread here, right? There is having some kind of spread between the points. So this is happening due to the reason there is some kind of multicollinearity present. Okay, there is some kind of multicollinearity present in our data set, in our data. Okay, so where is it in the, I mean, in the whole data, where is the multicollinearity present exactly? So we need to find that. So there are so many kind of methods, so I'll be explaining that. Okay, so this is the case. Yeah, and now, okay, so okay, you have got to know that there is some kind of, okay, you have got to know that there is a multicollinearity. You have got to know that there is some kind of multicollinearity in our data between independent variables. Okay, you have got to know this. There is some kind of multicollinearity between the independent variables in our data. So how to deal with this? Okay, so actually how to detect the multicollinearity first of all. Okay, you want to find out, not there is, but is there any multicollinearity in our data between the independent variables? You have a question like this. You have erased some kind of question like this. So how to find out? First of all, we need to find, right? Find, but how? How to find out that multicollinearity is there in our data set? So how to do that? How to find out? We can do that. Sorry. So we can do that by using the technique called PCA. Okay. So this is the principal component analysis. This is the principal component analysis. Using this principal component analysis, you can find out that uh, so you can find out that there is some kind of multicollinearity present in our dataset, and you can you try to, I mean, you can just delete those columns. Okay, you can just delete those variables. So these are all the methods, right? So these are all the methods. So okay, sorry for the confusion here. No worries, I'll explain it now this time. So how to find it? So we can find out that by using the VIF. So VIF is nothing but variance inflation factor here. So this is the VIF. So from the sklearn we can import this VIF, and using this VIF you can definitely detect the multicollinearity. Okay, and also using the PCA you can also which is nothing but the principal component analysis. Okay, so this is another method with which we can detect the multicollinearity. And after detecting, how do you proceed with that multicollinearity? Okay, you have got to know that yes, I have multicollinearity, but what to do now? Okay, I have found that there is multicollinearity in the data, but what to do now? You only have the two options here. Okay, you only can do two options. One thing is you can delete. Okay, you can delete those variables from your data sets manually. You can delete those variables from your dataset manually, or you can, you after performing this particular VIF, that is variance inflation factor, you can delete those variables which have, for which the VIF is higher. Okay, you can delete them accordingly, or else you can just ignore this multicollinearity. Why to ignore this multicollinearity? Why? Because what is your aim of building the machine learning model here? For example, I have built a machine learning model here, and my only aim is to uh, my only aim is to get the accuracy. Okay, I just want to know the what is the accuracy of my model. I just want to concentrate on this. Okay, I just want to know the what is the accuracy of my model. So multicollinearity won't be impacting our accuracy, so you can just ignore. if this is your if this is your purpose of building machine learning model, then you can just ignore multicollinearity. Okay, why? Because if because if accuracy is your goal. Okay, if accuracy is your goal, you can just ignore multicollinearity, because multicollinearity doesn't impact doesn't impact accuracy. Did you get that? So multicollinearity has zero effect on the accuracy. So if accuracy is only your goal of building machine learning model, you can just simply ignore the multicollinearity which is present in your data. Okay. Or if you want to interpret the model, that is, you want to understand the model, what is actually saying, or you want to interpret the model, then I mean, multicollinearity will be a big problem. So what you can do is you can just delete those particular variables. Okay. So this is the this is the way forward if you find any multicollinearity in your dataset. But I just want you to know uh, multicollinearity in a greater detail. So I'll explain that. Just have a look at here. So we have the multicollinearity, that is MC, in short MC we can call it as. Okay, in this multicollinearity we have two kinds of multicollinearity, that is structural. One thing is the structural multicollinearity, and what is meant by structural multicollinearity? So this occurs, okay, this occurs when we create the columns from the existing columns and build model using all the features. Okay, for example, I have my data set. Okay, I have my data set, and inside this data set I have some columns like x1. Okay, uh, okay, x1, x2, x3. I have these independent variables, only these independent variables, that is x1, x2, x3. And you have decided to create one other additional variable, that is x4, using these existing variables. That is, if you want to, if you have some kind of formula with you, like if you multiply x1 into x2, and if you add this x3 with you, with this product, then you will get x4. Okay, if you have some kind of formula like this, okay, no matter whatever may be the formula is, you have used all the existing variables or some of the existing variables, and you have created a new kind of variable. Okay, then your dataset might impact with the structural multicollinearity. That is, in your data you will end up having structural multicollinearity, which has been created when you do this kind of thing. That is, when you if you just create the new variable, if you just create a new variable out of the existing variables, then you will get this kind of sort of multicollinearity, which is structural one. Okay, for example, you will have another kind of a multicollinearity, which is the data multicollinearity. Okay, so how does this happen? this is this will this will occur by chance, naturally. Okay, so this particular multicollinearity will occur by chance, naturally. So what does that mean? No matter whatever may be the data set is, there occur some kind of multicollinearity naturally. For example, let's imagine uh okay so for example, you have some kind of data set, right? So you have some kind of data set like this. Okay, in this you have your dependent variable. Your dependent variable should be uh, for example, how many weight, okay, sorry, how many kilograms will I gain in the next 2 months? Okay, so nothing but the weight here. So I want to predict my weight in the next 2 months. Okay, so here what is your independent variables? What's your independent variables? Here we have uh, so these are all the intake, right? So these are all the intake, that is mean by the consumption of the human body. So if you as a human being, if you consume like so what should you need to consume in order to gain the weight? For example, the fat products, mm, maybe mm, maybe oily items. Okay, maybe oily items and fats. Okay, maybe oily items and fats, and some milk products. Okay, So if you consider all these things here, so is there any relation between the oil and weight here? Actually, weight is a separate, it's a kind of a metric to evaluate a person's weight. Okay. And when you see this particular variable, that is oil, it's actually a different thing. Okay. We use oil in cooking or in some other thing, right? But we won't use this weight is nothing but a metric. Actually, when you observe here, it's having no, I mean, there is no direct relationship. Okay. But what happens is, if you take, I mean, if you consume oils, okay, for example, if you are consuming some 2 liters of oil, I'm just saying it approximately. Okay. So if you just consume 2 liters of oil monthly, okay, then your weight will definitely increase by let's say some 5 kgs. Okay. If you consume some 4 liters of oil monthly, then your weight will definitely increase by 10 kgs. So here, if you are actually increasing the consumption of your oils, then your weight is actually increasing, right? So there is some kind of relationship, that's which is not a direct one. Okay. If when you look at here, oil is a liquid thing and weight is a metric here. This is not any physical term here. There is no direct relationship in between those two. Okay. But when the consumption of oil in your body is increasing, then automatically your weight is actually increasing. So there is some kind of directly, these two are directly proportional. I mean, maybe there is some kind of indirect relationship between these two. So that is nothing but a data multicollinearity. Okay. So what there is no direct relationship between the fats and the weight here. Okay. But when you consumption, when you increase the consumption of the fats here, maybe you are taking 3 grams of fat and 5 grams of fat here, automatically your weight will definitely increase by so and so weight. So that means this is a kind of a multicollinearity which is occurring by which is occurring by chance, that is naturally. So no matter whatever maybe the data set is, you definitely have some kind of relationship. Okay. See, I'll give you another example for the data multicollinearity. For example, uh, uh, okay. So for example, mm, human health. Okay, maybe no, not health here. So heart attack here. So you can say this heart attack. So this is the, let's imagine this is the probability of a person actually may affect with the heart attack. Okay, this is the probability of getting heart attack. And now you have so many variables like for example, you have the mobile here, phone, and you have the mm, you have your house very much closer. Okay, very close to the traffic. Okay, to the busy roads. Okay, you have this kind of two variables. When you look at here, the phone has nothing to do with the heart attack. Okay, because uh, this is a kind of electronic thing, and this is a kind of heart attack is nothing but it's a kind of a disease. This is not a physical item, but this is a physical item. When you look at this particular variable, that is house very close to the traffic, it is a physical item. But heart attack is not a physical item. But there is no correlation. There is no direct relationship with the, I mean, between the two. But when you seriously have a look, deeper look here, studies are actually saying the people who are actually talking much on the phone may prone to heart attack. There may be a chance of getting heart attack. Those who are actually speaking on the phone, I mean, studies are actually illustrating this. So there is some kind of a by chance relationship, right? So the relationship is actually here, the by chance here. That means it is actually occurring naturally. Okay. So we are not actually establishing the relationship, but the relationship has formed naturally by chance. And now, when you stay very close to the traffic here, then your chance of getting the heart attack would be definitely very high. Why? Because whenever you are built your house very much closer to the traffic, then obviously you'll be facing all the noise pollution in your daily life, then automatically there may be some kind of chance of getting heart attack. So this is a kind of data multicollinearity. Did you get that? Okay, so I have already explained, told you that how to detect the multicollinearity. Uh, Multicollinearity can be, I have forgot to mention one thing. Okay, data multicollinearity can be found using a pair plot also. We can also detect the multicollinearity using a pair plot, and we can also perform some variance inflation factor, that is VIF. Using these two, you can detect the multicollinearity. Okay, how do you detect the multicollinearity? Using pair plot and using the VIF also. Okay, VIF also. Okay, so what is the formula of the VIF here? So VIF is nothing but the formula is 1 by 1 minus r square. So what is the r square here? R square is nothing but the coefficient of determinant. We all know that. What is the range of r square? So r square lies between 0 to 1 here. So the r square value will usually lies between 0 to 1. Okay, so what is the relation between the r square and VIF here? So this is the formula. Based on this formula, so how do you establish a relationship between the VIF and r square here? So this is actually saying if if multicollinearity if multicollinearity between the variables is 0, then what happens? It's actually saying multicollinearity is 0. Okay, that means r is 0. R is nothing. What is meant by r? Pearson's coefficient. Pearson's correlation coefficient. He's saying r is 0. Okay, what happens if r is 0? R square will also become 0. Then what happens? R square will become 0. 1 minus 0. Then VIF is actually approaching 1, right? So 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 ultimately, if multicollinearity is 0, then r becomes 0. Okay, then ultimately r square becomes 0. Then ultimately, if you substitute the value of r square, that is 0, in this entire formula, you will get the 1 here. That means if multicollinearity is 0, that is, if you don't have any kind of multicollinearity in between the variables, the VIF value would be 1. Okay, but what if multicollinearity is some average? Okay, if what if the multicollinearity is having some average? So what happens? Okay, then then VIF will definitely becomes less than 1, but not equal to 1. Okay, remember this, never equal to 1. It should be less than 1. Why? Because MC is having some kind of higher value, that is average here. Okay, what happens if MC has a average value? Then r square will be higher. Okay, then r square will be approximately 1. Okay, let's imagine this, r square will be higher, then r will be higher, then r square will also be higher. That is, let's imagine 1 here. Okay, so what happens if I place 1 here? 1 minus 1 would be 0. So automatically 1 by 0 would be the case here. Okay, so 1 by 0 means automatically it's having something which is less than 1. The value would be this. What if multicollinearity between the variables is actually uh, high? Okay, very high. If the multicollinearity is high, then what happens? The VIF, the variance inflation factor, would become infinity. It approaches to infinity. It approaches to infinity. So what does that mean? So if multicollinearity is very high, damn high, then what happens? R square will also be very high. High means what happens? What happens here? So the denominator becomes 0. When we substitute the 1 here, it would become 0. Okay. Then 1 minus 1 would be 0. 1 by 0 would be, obviously, VIF becomes infinity, right? So this is the thing here. See, this is the general case here, but if you want to know what is the exact value, okay, then what is the exact value of the VIF, I'll explain you. See, if VIF equal to 1, okay, VIF will become 1 when there is no correlation between the independent variables. If there is no kind of correlation between the independent variables, then our VIF would become 1, and VIF will also between 1 and 5. It will lies between this range, that is 1 and 5. So when does it happen like this? If there is a moderate correlation, that is average correlation. If there is any average correlation between the variables, okay, uh, then I mean, what is meant by this moderate correlation? That means not having severe correlation. Okay, this is not a severe correlation. This is only a moderate correlation. That means, but not severe enough to. Okay, so not having severe correlation. Then VIF will be landing. The value of VIF will become in this between will lies in the range of 1 to 5. Okay, and what would be the third one here? So the VIF value will definitely become greater than 5. When does it happen? If there is a severe multicollinearity in our data set between the variables, then what happens? Then our correlation, I mean our coefficients, okay, our coefficients are poorly estimated. Why? Because it's having high collinearity. So that's why our model won't estimate the coefficients much, I mean, much perfectly. So it will calculate the coefficients much poorly. And what happens? Our then what happens? If the coefficients are poorly estimated, then we can't trust our p-values, right? So then our p-values are questionable. That is, we can't rely upon this p-values, right? Did you get that? So this is the thing here. And also I want to explain something, which is the first one is if multicollinearity is perfect. Okay, if multicollinearity is perfect, what happens? The regression coefficients of X, the coefficients of independent variables are indeterminate. So we can't determine our coefficients. Okay, then what happens? Their standard errors, okay, their standard errors would be infinity. Okay, what if multicollinearity is less perfect? Okay, it is not that perfect, but it is less perfect. What happens? The coefficients are determinate. Okay, then we can determine the coefficients. Coefficients are determinate, but but the standard errors would be large. Okay, standard errors would be large. Here the standard errors are greater than the large. That means they are actually approaching towards the infinity. But here, since the multicollinearity is not that perfect, this is somehow less than that perfect. Then then we can find out the standard errors in a large position, not that infinity, but somehow which is less than the infinity, that is large. Okay, see. remember these terms. That is, when it is perfect, standard errors would be approaching infinity. When MC, that is multicollinearity, is less than the perfect level, then what happens? Our standard errors would be large. Then the third, if MC is high, if multicollinearity is high, then what happens? Then this won't take the property of being best unbiased linear estimators. Okay, then what happens? It violates none of the regression assumptions. Okay, we will have the regression assumptions here. Usually for linear regression we have certain kind of assumptions. Okay, so that property will be violated if multicollinearity is very high. Okay, but it's hard to determine the coefficients with the small standard errors. Okay, coefficients are very hard. It's very hard actually. It's hard to determine. It's hard to determine coefficients because their their standard errors are very small. Okay, so this will be the scenario here. So this is the topic of multicollinearity. Okay, now I hope you have got some kind of good understanding about the multicollinearity. Why? Because I have already explained it theoretically, and now when you look at here, this would be the multicollinearity. This would be the process of detecting multicollinearity. That is nothing but the VIF. Okay, just observe here. What are the coefficients for the independent variables here? 0.39 something. Okay, 0.13. Okay, just check it now. What is the coefficients here? See the so this is the VIF value actually. Okay, why are you actually testing this particular thing here? Why? Because when you observe this particular graph, there is some kind of spread in the data. So that means you can definitely say that there is some kind of correlation. There is some kind of multicollinearity involved. So using this, importing this particular variance inflation factor from the stats models dot stats dot outliers influence. Okay, so what you can do is, this is a stats models library. So from that I'm just importing variance inflation factor here. Using running a simple for loop here, I got to know all my variance inflation factors for each of the independent variables. So cylinder is having 172, 87, all these are greater than 5, right? So what you can do is, you can just remove this particular first variable, that is the cylinder here. Then again if you run this particular entire thing again, then you will end up having different VIF for the displacement variable. And again, if it is greater than 5, you'll definitely remove that thing, right? So likewise, you will be end up ending up with only the best possible independent variables which have zero collinearity. Okay, then only your model will be a good fit. Okay, so this is the thing here. Okay, so yeah, that's all for this, and I'll see you in the next video. And in the next video I'll be focusing on the curse of dimensionality, and so there is a method that is a residual versus fitted plot here. So I'll be explaining that particular thing, which is very useful if you want to check the errors. Okay, and also I'll be explaining curse of dimensionality, and then I'll be explaining all the assumptions of the linear regression, and in the much later stage, further I'll be explaining the shrinkage models, that is lasso and ridge regression. So by this, we can definitely end up this linear regression playlist here. And later I'll be focusing on the model which is nothing but the logistic regression. That's a classification model. Okay, that's again a huge story. Okay, so yeah, that's all for this. I'll see you in the next video. Take care. Jai Hind.